We have the constant function f of x equals c, where c is a constant. It can be 2.5, it can be -1, but anyway, it's a. So if we just draw c like it's here at 2.5, this is the graph of it. It's a horizontal line. The domain, if you project it to the x-axis, x could be any number from -infinity to infinity. All real numbers, but we write it in interval notation. The range, project this to the y-axis, and since it can only be one number, we'll put it as set notation with the curly parentheses. It can only be one number, the range. And is this increasing, and what intervals is this increasing and decreasing? Constant, it's constant the whole time from -infinity to infinity. And is this function even, odd, or neither? And now we're just going to use the symmetry. This is symmetric with respect to the y-axis here, so it's even. If we flip it about the y-axis, it lands on itself. The identity function is f of x equals x. Or the line, you're probably used to seeing it as y equals x. So if we made a table of values, -3, you get -3. You put in -1, you get out -1. Whatever you put in for x, that's what you get out for y, etc. Okay, so you can make a table of values. You can graph that. It's the diagonal line here. That's it. This is the identity function. F of x equals x. You're going to need to know these functions, some of the common functions of algebra. The domain, project this to the x-axis. It keeps going at an angle to -infinity on x and positive infinity on x, so it's -infinity to positive infinity. Range, you project to the y-axis. It keeps going to -infinity for y, positive infinity on the y-axis on the other end. So we always put the smaller number first. The range is -infinity to infinity. And it's not decreasing or constant, it's increasing the whole time from -infinity to infinity. This is its whole domain. We're always talking, these are the x values where y is rising. Y is rising the whole time from left to right, so the x values are the whole domain. And this is odd. It's symmetric about the origin. Okay, so you flip it this way, and that way it lands on itself. It'll be down there and then over there. Okay, the absolute value function, f of x equals the absolute value of x. So the vertical lines. So the domain, all right, well, let's graph it first. Y equals the absolute value of x means if you got x, y, if you have -3 for x, it becomes positive. That's what the absolute value does. Whoops. If you got -1 for x, it becomes positive. The absolute value 0 is 0. 2 is 2. 5 is 5. It's the distance from the number line. Distances are always positive. So we got minus 3, 3, and minus 1, 1, 0, 0, 1, 1, 2, 2. It's a B. And this is the vertex at the origin. And that's the absolute value function. So you look at the domain, project it to the x-axis. It keeps going at an angle, so it's going to negative infinity on x this way. This way it's going to positive infinity, so the domain is minus infinity to infinity. The range projected to the y-axis, it does take on the value of its vertex. You can take the absolute value of 0. You do get 0. So it includes 0. So it's square bracket 0 infinity. And we never include the infinities. So it's never constant. You don't see it being flat anywhere. But it's increasing where it's rising from right to left. This part, but what are the x values? From 0 to positive infinity, and we always use parentheses. It's decreasing from left to right. Here it's falling. What are the x values? Minus infinity to 0. Any questions? All right, and then this is even function because it's symmetric about the y-axis. Flip it about y. You know, this is x, this is y. Flip it about y, and it leans on itself. Any questions, guys? Don't be afraid to ask questions or slow me down or anything. Okay. Are we still drawing, writing? Yes.
You said if it was even, it was symmetric to the y-axis. Okay.
Right. With respect to the y-axis. WRT means with respect to. Okay. Oh, no yawning. You'll have me falling asleep. I know, you guys are sitting down. That's going to be hard to say right now. All right, and then the standard quadratic function. The domain. Oh, well, let's say what it is. F of x equals x squared. In this class, we don't call this the square function. The square function. And I think they called it that in 1100. So we call it the standard quadratic function. X squared to its highest power is just x squared. And so if we make a table of values, if we have negative 3 and square that, we get positive 9. Negative 2 squared is 4. Negative 1 squared is 1. You can do that on your calculator. 0 squared is 0. And 2 squared is 4. And 3 squared is 9. I skipped 1, but I know it's there. Okay. This is called a parabola. The graph is called a parabola.
How did you start with the negative 3? Where did you get that from?
Oh, well, I knew if I started with negative 10, 100 wouldn't be on there.
So you just pick.
You just pick convenient values of x, and then you find y by squaring it.
Okay.
And you can square it on your calculator too. But when you square a -3 on your calculator, you have to have parentheses around it, because it's -3 times -3 gives you a positive. So I picked -3 because I knew -3 squared was +9, which is up here, and it's barely in my, this only goes up to 10. -2 is 4. Oh, that's -1. Whoops. -1 is 1. We got 0, 0, 1, 1. I didn't write that one down, but that's there. 2, 4. It's symmetric. 3, 9. And then you make a smooth, like ball-shaped, and it keeps going. It's got arrows, and that's a parabola. Okay, so what's the domain? This is going up at a sharp angle, but still it goes to -infinity. On x, positive infinity on y. So the domain is -infinity to infinity. So if you're going to guess the value for domain, that might be a good one to guess. Range, again, project to the y-axis, it does take on the value of its vertex. This is called its vertex. It's at the origin, and the vertex of the standard quadratic function is at the origin. The vertex is where it's changing from decreasing to increasing. Anytime a graph changes like that, it's called a vertex. It does take on its value of its vertex. So it's a square bracket, 0. Y can be 0 through positive infinity. Increasing, decreasing, or constant. Okay. It's never constant. There's no flat areas. But it's decreasing from -infinity, oh, let's write it. From -infinity to 0. It's changing at 0, so use a regular parentheses, and it's increasing from 0 to infinity. And it's even because it's symmetric about the y-axis. Flip it, it lands on itself. In the square root function, f of x equals the square root of x. So we can make a table of values. Now can we take, well, to draw a graph, if you try to take a square root of -1, can you draw that on this graph? No. So we got to start with 0 on this. Square root of 0 is 0. Square root of 1 is 1. And then we pick convenient values of x that have perfect square roots. So 4, square root of 4 is 2. And then, oh, we can't go any further than that. You know, we could put 9 and 3, but it goes off this graph. So we got 0, 0, 1, 1, 4, 2, and that's all this graph shows. It's got an arrow there. Okay? What's the domain? Project it to the x-axis, and it includes the 0, 0, the 0 here for x. So it's square bracket 0, infinity. What's the range? Projected to the y-axis. It includes the 0 for y, and it keeps going up at an angle to positive infinity. So the range is also 0 to infinity. And if you look at the graph, it's never decreasing from left to right or constant. It's increasing, and it's where its whole domain. Oh, we don't use square brackets either. 0 to infinity. It's increasing from 0 to infinity. at 0 is when it's starting, so we can't say that it's increasing right at 0. And this is this symmetric about y? No. Is it symmetric about the origin? No. It's neither. Okay, the standard cubic function. F of x equals x cubed. So we're going to pick some convenient values of x and y. So minus 3 cubed is 27. That's not on the graph. So minus 2 cubed gives you minus 8. You can do that on the calculator if you want. Minus 2 times itself 3 times is negative 8. Negative 1 gives you negative 1. 0 to the third power is 0. 1 to the third power is 1. 2 times itself 3 times is 8. 2 to the third is 8. So here's what this graph looks like. Negative 2, negative 8. Negative 1, 1, 0, 0, 1, 1, 2, 8. Okay, that's the standard cubic function. So what's the domain? Project to the x-axis. It's going down at an angle, but this way it's negative x. It keeps going even though it's at a steep angle. It keeps going. And this way also, so the domain is minus infinity to infinity. What's the range? Project to the y-axis. You can pretty easily see it's minus infinity to infinity. Increasing, decreasing, or constant. Look at the graph from left to right. It's always increasing. During its whole domain, it's minus infinity to infinity. And this is odd. This is an odd function. You can flip it about the x-axis and then about the y-axis. It lands. This half will land on itself. And the cube root function is f of x equals the cubed root of x. So we have x and y. We're just going to flip these things. The cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. The cube root of 0, 0. The cube root of 1 is 1. And the cube root of 8 is 2. So these are actually inverses, and we just switch the x's and the y's around. And so here's what it looks like. Minus 8, minus 2, minus 1, minus 1, 0, 0, 1, 1, 8, 2. And that's the cube root function. So projected to the x-axis, the domain is minus infinity to infinity. What's the range? Even though it's at an angle, the range, it's going at an angle, it keeps going both ways. The range is again minus infinity to infinity. And it's increasing, look at it left to right, it's increasing the whole time, the whole domain, minus infinity to infinity, and it's odd. You flip it about the x-axis, and then this half about it's down here, and it flips on top of itself. You flip it twice, about the two axes, it lands on itself. Any questions? Okay, so those are the common graphs. You need to be familiar with them. I ask you what's the square root function, you need to know that that's the square root f of x equals square root of x. So, okay, now I actually have a nearpod for this. So. Section 1.6 transformation. So this is the code. You're going to go to nearpod.com on your computer is probably the easiest. If you have an iPad with you, you can do that too. HQ, headquarters. Okay, this is the Nearpod that goes with this lecture. It's really nice when we have computers in this class. Okay, and go to nearpod.com and type in CBGHQ in the lesson code. Is everybody there? And I have complete control over your computer. No. Okay, you can just use the nickname. I'll probably put type name. Okay, transformation. There it is. Except that. We can join the code. Okay. Oh, you're on your phone with it? Okay. All right. So, this is what we're going to be doing. We're going to be shifting the graphs. So, if f is a function and c a positive number, the graph of y equals f of x plus c is the graph of y equals f of x shifted c units vertically upward. And the graph of f of x minus c is the graph y equals f of x shifted c units vertically downward. And what we've got is our function. We would start with one of those common functions like x squared. And if we're adding a constant on the outside, so if it's on the outside, it changes the y coordinate. So if you had x, y, and shifted it right by a positive number, it's going to be x, y, plus c. You're going to add c to every y coordinate to shift it. Okay? You can also, if you're shifting vertically downward, you're going to subtract c. So x, y is going to become x, y minus c. and that's a vertical shift. So a change on the outside changes y. The function is here, and we're adding c outside the function. So, and then horizontal shifts, let's see. Now we're inside the function. See, we're inside that notation. So if a change occurs on the inside of the function, it changes x. And it changes x in the opposite way you would think. So when you're adding c on the inside, that's the graph of y equals f of x shifted left c units. And when we're subtracting c on the inside, that's the graph of y equals f of x shifted right c units. And there's an example. If you have the function, the absolute value of x, and you want to do absolute value of x plus c, 3, the 3 is on the outside, not inside the absolute value signs. So it's going to change y. So you shift the graph up 3 units. So instead of 0, 0, we're at 0, 3, etc. So there's an example. Here's another one. Here's a horizontal shift example. If we start with the square root of x and we subtract 4 on the inside, that changes x. It shifts to the right 4. So instead of at 0, 0, we're going to start at 4, 0. Right 4 units. So that's the original function and the next one. Oh, there's the answers. Let's see if you can do this. I made mine small. You got a little thing, fill in the blanks to do, right? You got to grab with your mouse the little things and put them in the right place. And I was just displaying the answers, but yeah. See if you're awake. Oh.
What was the code? Mine knocked me off for some reason.
Oh, it's right there. CVGHQ. The first blank is supposed to be, you know, up, down, right, or left, and then the next blank is the numbers. So it's gonna, you're not going to say shifted 3 up units. So there we go. Okay. So a little fill in the blank for you to do. I forgot. I have to hide the names and it wouldn't show the answers then, right? Okay. Was that there? Oh, yeah. Did you guys finish? When you finish, you hit done. And if you were doing, let's hide the stupid names. Now it won't show the answers. Now, if I may, you know, assign a self-paced Nearpod at some point. If you're doing a self-paced one, you get to control the navigation. So these go to the next slide, the arrows up here. But if, on something like this, if you don't participate, I'm just putting them anywhere. If you don't participate, it's going to tell me you didn't move these things. But down, right, yeah. Now you know this is wrong, but if you hit done, I got 1 answer out of 8. And then you close it. So you should have got 8 answers out of 8. So, did everybody finish? And no, that's not right what I have. You done? All right, and then a self-paced one, you could keep going. You could do it yourself, but you want to move the boxes and then hit done before you hit the right arrow. All right, so you just did these examples. So this was up 3, this was right 5, this was left 2, and this was down 4. So that's your fill in the blank with these examples, wasn't it? All right. Reflections. Oh, I have an example to do before reflections. That's the next one. Okay, so forgot the little example slide apparently. So we can do this example. So what if you have the graph absolute value of x and you want to shift, you're subtracting 3, it's on the inside, that means it changes x and it shifts it the opposite way you would think. Subtracting shifts it to the right 3 units. So we got absolute value of x looked like a V. This is, okay, that's an absolute value of x. So we can shift right 3 units. We're going to shift the vertex right 3 units, 1, 2, 3, and it goes at a slope of 1 and -1 here. And this is the absolute value of x minus 3. You could also, write some points, 0, 0 on here, and say 1, 1. You're going to subtract, you're going to add 3 to each x coordinate, so it's going to be 3, 0 for the vertex, and 4, 1 for the next point. If you're doing this in my math lab, you will need, it will ask, sometimes it will ask you to shift right 3. Sometimes it will ask you to graph it. You'll have to choose the absolute value function, click on the vertex, and then one other point to graph it sometimes in MATLAB. Okay? And then adding 2 on the outside, so it changes y. So you have to memorize this. Outside, it changes y. Okay, so we are, and it's a shift up 2. So we, again, are starting with our absolute value. But now we're shifting up 2, so we're going to go from 0, 0 to, and from 1, 1, we're going to add 2 to the y coordinate. So we're going to go to 0, 2, and 1, 3. Oh, you can't see that. So 0, 2 is now the vertex, and 1, 3 is another point, and it's a V. So memorize, if it's on the outside, it changes y. You can add or subtract the coordinate. And if you actually need to pick points and follow it like that, you always want to pick the vertex and one other convenient point. So, any questions? Okay, now we're on reflection. So that was the next slide. Okay, so if we have the minus sign on the outside of the function, this is on the outside, it changes y. Okay, but it changes the sign of every y coordinate. But if you change the sign of every y coordinate, which axis are you reflecting across? If you are up here and you change the sign, say this is 1, 1, well when you change the sign of the y coordinate, you get 1, -1. So you're flipping about the x-axis. So it does change the sign of every y coordinate, but it's a reflection about the x-axis. And now this is on the inside. It changes x. In fact, you would change the sign of every x coordinate. So our little slideshow says that if you have x, y, it's now going to be -x, y. And up here, if you had x, y, it will be x, -y. And that's the y-axis, actually. You're reflecting about the y-axis. If the negative sign's inside the function, you're reflecting about the x-axis if it's outside. Okay. This is an example from the book, and it's actually a function that would look the same no matter which axis you reflected about. So it's not a very good example, but it is reflecting, it's on the inside, it's reflecting about, wait a minute, that's got a typo on it. The negative sign's on the inside, so it's reflected about which axis? The y-axis, right? When you change the sign of every x coordinate. So let's start with something like the square root function. And this is the point 1, 1. And this is 0, 0. So 1, 1 will now become, for flipping across the, the change on the inside, -1, 1. And 0, 0 stays where it is, -1, 1. That's flipped about the y-axis. So there's a typo on our slideshow, but the graph they chose to show you would have looked the same no matter which way it was reflected. But so that should say y-axis. Okay, you have a little quiz. So you gotta click go, and it's just a couple questions, and I don't even see the questions. So these Nearpods are like PowerPoints on steroids. They can. So you're actually doing the next two questions. All right, good. Did everybody? You're in your notes. You're the next two questions. Everybody do it? Okay. Good. Done. All right. All right. So I'm going to share. Has everybody answered? Still answering. Okay. And we don't show your name, so you share this. You guys can see how you did now. And I think was the first question, what's this transformation? That's the y-axis, right? And this is the x-axis. Okay. All right, so there were just two questions. Is everybody done looking at that? Oh, or is it a poll? Is it just a poll or a quiz? Oh, I probably already gave you the answer to this one. Okay, it was just a poll. Okay. Well, some of you aren't getting it right when I have the answer up here. Let's not be paying attention. Okay. All right. You done? Oh, I share. I'll hit share. So you just answered the left. That's a reflection about the x-axis. And it does let you answer two answers. Okay, now I have an example on the notes. So, all right. So if we're going to graph this function, we're going to show step by step what happens. So we're going to label these points: -5, 4, 1, -3, and 2, 2, and 5, 2. Okay, so we're going to start with this figure each time. And then we're going to start with this figure and do that. And start with this figure and do that one. Okay, so the change is on the outside. It changes the sign of every y coordinate. Okay, so I'm going to write my points down. -5, 4, 1, -3, 2, 2, and 5, 2. Changing those sign only the y coordinate, you get -5, -4, 1, 3, 2, negative 2, and 5, negative 2. Just changing the y coordinates. Now I can draw these lines, dots, and connect the dots. Minus 5, negative 4. And see if it makes sense. That's reflection about the x-axis. One, 3, 2, negative 2, 5, negative 2. So each of these was just connected with a straight line. And we've got it. Did that make sense? For what we had up here? We're reflecting about the x-axis. So this point should come down here, and it did. This point should go up there, and it did. And this line goes down. So that made sense, okay? But that's how you do it with points. You can also just try to move it. Think about reflecting it. Okay, what's the next one? This is on the inside. It changes, and it's a negative sign, so it changes the sign of every y coordinate. So again, we're going to start with the original figure. Oh, I said the wrong thing. X coordinate. Inside it changes x. So we're going to start with this same point. And we're only going to change the sign of x, so that's going to be positive 5, 4, negative 1, negative 3, negative 2, 2, and negative 5, 2. Okay? So 5, 4, negative 1, negative 3, negative 2, positive 2, negative 5, positive 2. Connect the dots. Did that make sense for flipping about the y-axis? If we look back at our figure, we're going about the y. This should show up over here. This should be over here. These should be over here. And it did. All right. And the last one is doing two transformations. So I recommend that you do your reflections first, and then you're going to do, this is a horizontal shift. So this is reflect. Number 1 is reflect about the x-axis. And the second step is shift left 1. Okay? So we actually already did the first step. It's here. So then if we just take this and move it left 1, and I can even just draw it over here, it's going to be here, 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 and here. So it's at -6, -4, 0, 3, 1, -2, and 4, -2. And so that's, but you could subtract 1 from each x coordinate after you reflect it. And sometimes I want you to show the progression of steps. So you're going to show the reflection first on one graph, and then you can show the shift on the next one. Okay? So, and I could have also drawn out these, where that went to. Subtract 1 from each x coordinate. -6, -4, 0, 3, 1, and we got it. It's there. Okay? Any questions? No? All right. Wow, it is long. We've been going a long time. We have, that's vertical and sequences, that's why. So, we want to pause it, take a break. We've been going a long time. Unpause it. Okay, let's see where we are in the slideshow. Finish that example.
Did you just not all it? Thought I heard something.
Okay, so this is vertical stretching and shrinking. If we've got C, a positive real number, C, if C is greater than 1, the graph of y equals C times f of x is, we're multiplying by C on the outside. Which one's it going to change? Y. Okay. So C times f of x is a graph of y equals f of x vertically stretched. By multiplying each of its y coordinates by C. So on the slideshow, is it showing? Yeah, it shows that the point x, y becomes x. Well, they used A, but we're using C, C times y. Okay. If C, though, is between 0 and 1, then the graph of C times f of x is the graph of y equals f of x vertically shrunk or compressed. By multiplying each of its y coordinates by C. So we still multiply each of the y coordinates by C. So this is good for either one of these. And there's the picture of what's happening. So there's an example. If we've got 2 times the absolute value of x, it's the red line. We're multiplying each y coordinate by 2. So the point 0, 0 stays there, but the point 1, 1 becomes 1, 2. It's a red line. Horizontal stretching or compressing, the next box. Y equals C times x, where C is a positive real number. The C is on the inside, that changes x. And if C is greater than 0, let's see, we're going to be, if C is greater than 1, it's the graph of y equals f of x horizontally shrunk. And it shows shrinking here. And it's stretching on this side if C is between 0 and 1. And and we divide each of its x coordinates by c. So x, y, in both cases becomes x divided by b, comma, y. Oh, c, you know, I'm looking at the slideshow. On the notes, we have the constant in c. So we have to divide. And so if we divide by a number more than 1, we're making the period smaller. If we're dividing by a number that's a fraction between 0 and 1, that becomes a larger number and we stretch. Okay, so they're showing you a sequence of transformations then. And I don't agree with their order. Okay, so what we want to do is, well, this doesn't have reflections. I guess if it doesn't have reflections, the order is not so important. But you should do your reflections first, and then you do your horizontally. Let's just go to the next one. It's showing these. I do my reflections first, then my horizontal shift, stretch or compress, and then the vertical shift. So I do my reflections first. So what did I say on the next page? You can do it in this order, but you could also do reflections first, and that works pretty good. Do reflections first, and then you do them in that order. If you do a vertical shift before a reflection about the x-axis, it's going to mess you up. All right, so we're going to use the graph of y equals f of x equals the square root of x to graph the function g. So the next slide is showing you some stuff. Another example. Oh, and that's the last one. Well, I'm going to do this example. And then, okay, so we've got the square root of x function right here. And I had trouble drawing it because I actually brought this graph, this thing, and tried to do it in Paint, Windows Paint. Okay, that's what I did. Windows Paint. Okay, so here's y equals f of x, and here's some key points. All right, so we're going to graph this. We're going to do the reflection first about the x-axis, and then we are going to do a horizontal shift left 1, and then we're going to shift down 2. Here's what it looks like in the calculator. Okay, so we got 3 steps. Here's the original function. We're going to reflect it about the x-axis. So 0, 0 is still at 0, 0. To reflect it about the x, we change the sign of every y coordinate. So I could actually show you 0, 0, 1, 1, 4, 2. Changes to 0, 0. We're reflecting about the x-axis. Change the sign of every y coordinate. And if we graph that, 0, 0, 1, negative 1. Yeah, that's right. and 4, -2. There's our function after reflecting about the x-axis. Reflect, about x-axis. Now we want to take that and we want to shift left 1. That means that we're going to subtract 1 from each x coordinate. So -1, 0, 0, -1, and 3, -2. Y stays the same. So we're actually shifting left 1. We should be here, and then here, and then at 3, -2. And so we shifted left 1. And then shift down 2. Would be subtracting 2 from each y coordinate. If you want to write it out, -1, -2, 0 stays the same, -3, and 3, -4, and you just go down 2, down 2, down 2. And that's what you get. You can check that in your calculator. Yes.
Is the third one still called the horizontal shift?
This is a vertical shift down to.
And the middle one is horizontal?
Yeah.
Okay.
Okay. We were doing, and you know, I changed the sign of every y coordinate. Coordinate here. I subtracted 1 from every x coordinate. And then I subtracted 2 from every y coordinate. I was doing it in my head, so I don't know if you were following. So you can do it that way, you can do it this way, and sometimes MATLAB makes you. But I do like to see what you're doing at each step. And since we started with the square root of x function, what is it doing Dropbox? What? Just set up Dropbox. Does it have a mind of its own or what? I think so. I don't think I need to set up Dropbox, but then you can check. Y equals, clear it out. Negative second square root x plus 1, close the parenthesis, and then subtract 2. We have to close the parenthesis so we're outside. We can hit graph. I don't know where it's set up at. It's not very nice. Let's do zoom decimal. No, zoom standard. Zoom 6. -10 to 10. It's hard to tell, but that's the same function. We could have set it up the same to show the same, but okay, so you can check your final result in the calculator. Any questions? All right, so describe the steps for each transformation. What are we doing here? We're going down to units. Here, we're going to reflect about x-axis, and then we're going to go up to. Here is a reflection again about the x-axis. And then number 2 is a vertical stretch. You're going to multiply. Here, let's make this big again. You're going to multiply each y coordinate by 2 after you do the reflection. Okay, and this last one is, you want to rewrite this as 1/3 f of negative x minus 1. Now we can do our reflect about the y-axis. And then we can do the horizontal is subtracting 1 is shift right 1. And the last one is a vertical shrink. We're multiplying each y coordinate by a half. Or compressing vertical compression. Okay, and this is long. Okay, and then the last, are you done writing now? We're on the last page. I have to repeat the same lecture 3 times this semester. That's why I start skipping. Okay. We're done? Can you read that? And then, so here's a little exercise of some of these in the book. Here we have f of x is actually absolute value of x are graphed in the same rectangular coordinate system. If g is obtained from x through a sequence of transformations, find an equation for g. So we would want to shift left 2, and then it's a reflection about the x-axis. And when you're reflecting about the x, it changes y. So g of x is going to be, the subtraction sign is outside the square, oh, it's not square root, absolute value. And we're going to be shifting left 2 is adding 2 on the inside. Oh, that's our g of x. You know, if we wrote it with just f of x, it looks like this. But if we actually write it with the absolute value, it's like that. Okay, this next one, B, this is the square root function. So it looks like we reflected about the y-axis. That changes x, so the negative is on the inside. So that would be square root of negative x. And then step 2, we have to shift down 1, 2, 3, 4 units. And that's our g of x. So g of x equals square root of negative x, and shifting down is that's on the outside. We're outside the square root function. And then the last one, f of x is x squared, standard quadratic function. So we must have shifted about the x-axis or reflected. So we had x squared, we're going to have minus x squared. It's on the outside for x-axis. And then we have to shift the vertex to the right 3. So that would be inside the function x minus 3 squared. I've got to put it inside the squared, subtracting 3. And now we have to shift up 1. So we're going to have g of x is minus x minus 3 squared plus 1. Oh, so the very last thing is the last slide has you do this. You got the absolute value of x, write an equation for the graph as you do these things. Three units down, but we should have done the reflection first. So, minus absolute value of x. No, it's shifted over the x-axis. So, minus absolute value of x. 4 units left. It's inside the function. X plus 4 is left. Stretch vertically by 2. That's on the outside. And then 3 units down. Minus 2 absolute value x plus 4 minus 3. That's number 4. All right, and we're done for today. Any questions? All right, so can you print your tests out, or you just refer to them on Chobi? Your test is on Chobi. Everybody understand that? So, and you have different versions.